Hello and welcome everyone. My name is Peter Robinson and this is the Ethereum Engineering Group Meetup. Today we've got Leo, who is from Cavalry, who's going to talk about automatic market makers. So Leo, please introduce yourself to everyone, please.
Hi, I'm Leo Lau. I'm a quantitative researcher at Cavalry. I just got back to DeFi about less than 2 months ago. Before that, I'm mainly working on tokenomics and game economy design for and also blockchain gaming incubation and investing. And before tokenomics design, I did a little research on automated market makers and wrote an article on AMMs, and that's why Peter got interested and asked me whether if I can give a talk on automatic market makers. Yeah, so I've been in the crypto space for almost 2 years, but not quite.
All right, cool. Could you please share your slides? And are you happy for people to ask questions at any point, or should they wait till the end?
Yeah, I like to be asked questions during like interruption is good.
Okay, all right, sounds good.
For understanding.
Yeah.
Bye.
So today I will be giving an introduction on automated market makers, all kinds of automated market makers, basically an overview. So this is the outline of the talk. I will first discuss 4 kinds of constant function market makers and 3 ways to evaluate those automated market makers, and some advanced AMMs like TWAMMs and self-financing AMMs and time-dependent AMMs. And also we'll discuss a little bit of the routing problems if you have fragmented liquidity. So what is AMM? AMM is basically used by a decentralized exchange using a peer-to-pool model. So all the fund is deposited in a liquidity pool, and they use a pricing algorithm, which is the core of the AMM, to determine how the AMM should transition from one state to another, be it either for staking, like deposit liquidity, or unstaking, or swap. It should all be determined by the pricing algorithm. And you can view automated market maker as a rebalancing portfolio. So basically, when people trade against your the liquidity pool, the reserve numbers changes. Basically, you're rebalancing your portfolio that way. So first is Bancor. They use a bounding curve and a network token called BNT. So they only have they have multiple two token pools, and in each token pool, the token is paired with only the network token. So whenever you do a swap, you have to go through the network token first, and then go to your destination token. So in the graph, you can see they define like a constant called the connector rate, which is a ratio between the reserve of the token and the total value of the network token, determined by this first formula. So F is basically the connector rate. P is a relative price between the network token and the how to say, they say they use a smart token in the white paper, so I will use it. So P is the smart token price measured in the network token BNT. So if you do some kind of calculus on the product, use product rule on the derivatives, you can arrive at the following equations. So P is defined as a marginal price between the network token and the smart token reserve. Like it's a marginal price because you take the derivative. So so the bottom two equations is how you conduct trade. Either you input BNT tokens or you input smart token to get either smart token or BNT token. So say you have if you have two token pool, one with asset A and token BNT, and the other one with token B with and asset B and token BNT, and they have different connector rate. If you want to swap from token A to token B, you have to perform two trade. First, you need to swap token A to token BNT, which is denoted by the second last equation. And secondly, you need to swap the token BNT to token B using the trading formula provided in the last slide. And the relative marginal price can be expressed as marginal price of the relative marginal price of token A divided by the relative marginal price of token B relative to token BNT. So next I will talk about Uniswap. So instead of everything paired with network token, now you don't have this constraint. You can pair any token with any token. So they use a very simple formula, which is x times y equals k, which I write as the liquidity of the pool squared, which is, so the first equation is Uniswap V2, and the second equation is Uniswap V3. For Uniswap V3, they introduced a kind of virtual reserve. So, so the first, for x plus liquidity divided by square root of price B is equivalent to a virtual reserve of X virtual, and similarly Y plus L times price PA is a virtual reserve called a Y virtual. So effectively this this is effectively trading at Uniswap V2 function with X virtual times Y virtual equals L squared in this price range, PA and PB. If you go out of this range, the one of the reserve will go to 0, and the boundary can be easily calculated by setting either X or Y to be 0. You can also view this Uniswap V2 function as a simple translating function, like you shift the Uniswap V2 function to the left by L divided by square root of PB, and down by the L times square root of PA. So it's not very hard to calculate to prove that the value of 2 tokens in Uniswap V2 is equal. So the marginal price can be written as a minus derivative of dy divided by dx. And using the variant formula xy equals k, you can derive p equals y divided by x, which is a relative price between a relative price of x measured in y. So we have px equals py, px equals y. P equals the price of x divided by price of y. So you have the value of 2 tokens equal. So this is a further illustration of how to transition from Uniswap V2 to Uniswap V3. So basically, you introduce virtual reserves, or like shift the constant. You shift the xy equals k curve down and left, so it will intersect with the x-axis and y-axis. And using the Uniswap V3 formula, we can determine where the boundary are. So the boundary, so effectively you are just providing liquidity a price range. So on the right graph, you can see for Uniswap, because there's no limit, the reserve can go 0 to infinity. So the liquidity is uniformly distributed across all prices. But because of this translating function, the reserves can go to 0 when you go out of the price ranges. So you are effectively only providing liquidity in a price range. And it's also not hard to prove that the liquidity in the same price ranges are fungible. So, for example, the first depositor deposit quantity of X1 asset of X1 quantity of asset 1 and Y1 quantity of asset asset 2, sorry, and depositor 2 deposit X2 quantity of asset 1 and Y2 quantity of asset 2. And because of they have the same deposit in the same price range. They PB for them is equal. So some simple math, you can just add x1, the virtual reserve together, and the outcome is you can, which is the outcome is effectively adding their liquidity together. So big P here is the current price. So you can write the virtual reserves as a function of the current price, because the virtual reserves behave exactly same as the Uniswap V2 with no boundary. So basically we proved liquidity in the same price range is fungible. So you can basically add all the tokens together in the same price range together instead of worrying about them individually. Depositing liquidity on Uniswap V3 is also a little bit different compared to Uniswap V2. So Uniswap V2, you only need to deposit 2 tokens with equal value, but and the value is determined by the current price. But because of this translating shifting of the market maker, say if you want to deposit the X number of token 1 and Y number of token 2, the number of token 2 you need to deposit is not as simple as X times P, which is more a little bit more complicated. Which this effectively says that depositing liquidity, you don't deposit liquidity with the same value in Uniswap V3 because of concentrated liquidity. Because you can set any price range you want and put your liquidity there. This effectively supports range order. So when you have a price range outside the current price, because of the shape of the curve, you only need to deposit one side of the liquidity, because the other one goes to 0 as the price is currently outside your price range. So range order basically supports single-sided staking and 2 types of limit orders common in regular central limit order books. When the price completely crosses your price range, you can convert your one token to another token at a higher price, or buy one token using the other token at a lower price. So basically, you only need to single-sided staking one liquidity, and you achieve like token conversion from one token to another. Next, I will talk about balancer, which is a generalized form of Uniswap V2. So instead of having 2 tokens in one pool, you can have like n assets in one pool with value weights. So omega 1 to omega n is value of each asset divided by the total value of the liquidity pool. And the value of the asset n can be written as a value of the reserve of the asset n times the price of the asset and denominated in some token. And the relative price to itself, T token to itself is always 1. So you can write the you can also write the price of the token n in terms of token T as a ratio of reserves between token T and token N times their reserve ratio. So for Uniswap V2, it's just 2 tokens. So omega 1 equals omega 2 equals 1/2, because they always have the same. The 2 tokens for Uniswap V2 always have the same value. So the marginal price can be reduced similarly to Uniswap V2 as y divided by x. And it's also can be proved that the invariant formula for this AMM can be proved as this form. The balance of each token to the value weight of their respective value weight. The product of them is a constant. So for Uniswap V2, you can see omega 1 equals omega 2 equals 1/2. So basically, it's saying the geometric mean of the 2 reserves is a constant. So Uniswap V2 can be derived from a generalized balancer. So these are the trading formula for balancer for different conditions given either price or input token number or output token number. Next, I will talk about the curve, which is a combination of constant sum market maker and constant product market maker. So constant sum market maker is basically just a straight line or a hyperdimensional plane. Depends on how many tokens you are dealing with. The price doesn't, the slope doesn't change at all. Constant product market maker is basically Uniswap V2 or in general balancing with equal value weights. The curve combines those 2 market makers together to facilitate for stable. So curve V1 is for stable coins, and curve V2 is more general for general assets. For curve V1, they only have they facilitate trading mostly at the price of one because it's between stable coins. As you can see from this figure, it's like a Uniswap V2 function flattened against the x plus y equals constant line, and this is this gives a better price execution when the trading amount is not very large, which is so you don't want too much slippage when you put in stable coins. So they effectively concentrate the liquidity to price around one. But they are not using simple virtual reserves. They are using like weighted sum of constant sum market maker and constant product market maker. For curve V2, they reduced the amount of concentration around the price of one. So, and they can be tagged to any price instead of just one, as you can see from this figure on the right. So what they effectively does is concentrate the liquidity around the pegged price, and it's like between two Uniswap V2 curves. As you can see from this figure, the two Uniswap V2 curves are dashed, and the blue curve is the curve V1, which is a stable swap function. So they relax the concentration a little bit, so it's between two Uniswap V2 curves. So for curve V1, so they introduced the amplification constant called A, and a measure of how far away you are from the pegged price, which is one in curve V1. So for example, if you have n assets at equilibrium, all assets, the sum of all assets is D, and because the equilibrium is everything is pegged to one, so the product of all token reserves is simply D over n to the power of n. As you move away from the equilibrium, you will the effect of constant sum market maker should diminish, and the effect of constant product maker should increase. So to achieve this, they introduced not constant, but a coefficient called chi, which is the amplification factor A times the product of all token reserves divided by the equilibrium product, which is D over n to the power of n. So at the equilibrium, it's very easy to show that chi is equal to A. But when you have an imbalance and take a limit, say like one token goes to infinity, the chi will go to 0 because of because because the other asset will simply go to zero, so the product will approach zero that way. So chi approaches zero. So what this effectively does is when the token pool is imbalanced, which means it's the price is deducted from one. The market maker behaves much more like a constant product market maker. But around equilibrium, because of the amplification factor, it behaves more like a constant sum market maker. And we can calculate how to execute a swap on curve V1. Say if we want to trade assets, some assets like say XI for asset I to asset J. So we escalate the token reserve for asset J first from this from the second last equation. And we can rewrite the formula as a quadratic function. So everything here except the new reserve number of Sij is known. So B, C, and can be calculated. Those since there's no like quadratic formula on library on in Solidity, so they use the Newton's method to calculate what the new reserve token reserve for Sij should be. So basically, taking the derivative of the function and use a slope to find the intersection between the x-axis and the slope function which goes through the previous route. So by this iteration, we can find the new asset reserves. Once you get the new asset reserves, the difference between the past asset reserves and previous asset reserves of J and new reserves of asset J is the trading outcome you are getting. So for curve V2, instead of multiplying by a constant, not a constant, multiply by a constant vector A. They multiply another coefficient to the factor A, which is gamma squared divided by gamma plus 1 minus K0 squared. So K0 is simply the product of all token reserves divided by the equilibrium product. So why they do that is, as I said before, to relax the concentration a little bit, or introduce a new degree of freedom to reduce the concentration so that it not only serves stable coins, but also serves general assets with any pegged price. So the process is so gamma here is also constant. So curve V1 only have one constant A. For curve V2, you have two constants A and gamma. So the process of solving the trading outcome is similar, but a little bit more complicated. But still using you can still use Newton's method to get the trading the new updated reserve token reserve numbers and the differences for trading outcome. So this is a graph of A times K0 times this newly introduced coefficient. So basically, this is the y-axis is K and the horizontal axis is K0. Because you only have one constant in curve V1, so the relation between chi and K0 is a straight line. But when you introduce gamma, you have a nonlinear relation between K0 and K. So this is effectively it does is reduce the concentration. So the lower the gamma is, the lower the gamma is, the more quickly the constant sum market maker part goes to 0 or approaches 0 when the pool goes to imbalanced from the pegged price. If you have a higher gamma, if you have a higher gamma, if it approaches the constant sum market maker part will approaches 0 more slowly. So say if you have a price peg and you have n assets from an oracle, so you have P1 to Pn, and you first construct a equilibrium point where the pegged price, the pegged price times the equilibrium reserve are equal for all assets, which means value is equal for all assets at equilibrium. So take a two token pool as a simple example. So you only have one price, relative price. So at equilibrium, you only have P x0 times P times x0 equals y0. Plug into the general form of AMM, you have KD times PX plus Y plus PXY equals KD squared plus D divided by 2 squared. And because the current reserve is pegged to this price, it has to be on the market maker curve. So so you can solve for K0 and K. And after some tedious calculation, you can arrive at a very complicated formula for two assets. I think it's a 6 degree polynomial. So here everything is known except X and Y. So P is the current pegged price. D is the sum of two assets at equilibrium, which is given as a 2 or y0 if you took the relative prices denominated in token y. And yeah, so this is a 6-degree constant function market maker, and it's changing shape because after trading, the Oracle updates its price, so you have to repack the current reserves to a new price. So it's a constant function market maker, but it will change according to the Oracle. So here's a graph comparing the three market makers: Curve V2, Curve V1, which is a stable swap, and constant product market maker, which is a Uniswap V2. So you can see what Curve V2 does is only introduce a little bit concentration between the equilibrium equilibrium reserve, and when you go outside of the equilibrium reserve, it quickly becomes a constant product market maker. But for curve V1, when you have only 1 degree of freedom, which is only the amplification factor A, you can only achieve like constant product market maker behavior at very imbalanced reserves, which is not suitable for general assets. You don't want to trade assets at a fixed price, for except for stable coins. So here is exactly how they update their oracles. So you have some previous price in the oracle, and when the swap happens, you record the swap price, and it's basically weighted sum of the previous price and the current swap price. And they also, because they have two because they have two regions where one region behaves more like a constant sum market maker, and the other region behaves more like a constant product market maker. They have a dynamic fee model as well to compensate for that. So if the reserve is near the pegged price, they use a fee called F-made, and if it's very imbalanced, they use a fee called F-out. I think it's F-out for curve V2 40 BPS, and F-made for curve V2 is 4 BPS. And G is basically a measure of how far away you are from the pegged price. So if G is 1, it means you are on the equilibrium. So your fee is a minimum. So if you took some values and plot this fee function with respect to one reserve number, assuming there are only 2 tokens in the pool, using the 6 degree polynomial I just showed earlier. You can see exactly what I just talked about. The phi approaches minimum at the equilibrium reserve and becomes larger and larger when you go out of equilibrium. Oh, sorry. So the F out is 40 BPS, but for F mid is 5 BPS. Or it's not 40. Actually, it's 4 BPS. Never mind. Yeah. So next, I will introduce some like standard people use to analyze automated market makers. One is called the impermanent loss. So it's basically the difference between the LP value, which is your rebalanced portfolio, minus if you just don't rebalance your portfolio but hold the original tokens you want to deposit. The difference of value is an impermanent loss. So for Uniswap V2, the impermanent loss function looks like this. K is a measure of the duration from the current price, and the y-axis ILK is a measure of impermanent loss in percentage. So basically, LP minus HODL divided by the HODL value. So to derive this formula for Uniswap V2, we do some simple calculation, and so here we introduce the K parameter, which is the ratio between the new price and the old price. So the value of LP can be written as the current price times the current price times the current reserves minus the current price times the reserves if you don't you start with. So you simply, if you don't deposit, how much value would it get at the current value, at the current price, and substituting the expression for X and Y using the current price, which is P times K. You can cancel the square root of P times L part and arrive at this simple formula. Because this is always less or equal to 0 because it's a simplified Jensen's equation. So this or I should say like A plus B is always larger than 2 times square root of A times B. So the arithmetic mean is always larger than the geometric mean of 2 numbers. So this is always less or equal to 0, which means if the price deviates from the current price, compared to a model profile, you will always get some loss. So So this is the expression for Uniswap V2. For Uniswap V3 is a little bit more complicated because you have to take into consideration whether the price moves out of the price range or not. So if the price is in range, the impermanent loss formula is like this, and R1 and R2 is the ratio between the R1 is the ratio between the current price divided by the lower price bound of the price range, and R2 is the ratio between the higher price bound of the price range divided by the current price. So when you have the current actually when you have the current price outside the price range to the left, you get the impermanent loss equation of the second line. And when you have a current price outside the price range on the right, you get a new impermanent loss function. They all connected as a boundary, so it's not discontinuous. So the limit of each of these three functions connected at when the price crosses the price range. And there's another criteria to analyze how LP performs in how LP performs compared to a rebalancing index. So basically, losses versus rebalancing can be thought of as the difference between execution price by the arbitrator and the market price, and A times the volume of the trade. So, so you can think of this as if you execute this price, execute this trade at market price instead of execute it on the executed on the AMM and take the price difference as a profit. How much money does the arbitrator make? And the gain of the arbitrator is the loss of the LP. And when you have multiple assets, you can just add a summation sign up to the left. So it's a sum of your portfolio, each asset in your portfolio, the volume times your difference between the execution price on the AMM and the actual market price. So there are two assumptions made in both the impermanent loss and loss versus rebalancing standard or criteria. So first is market price is equal to the post trade marginal price. So there, so they always arbitrate arbitrators to bring the post trade marginal price of the AMM to the market price. And another assumption is transacting at the market price has no slippage. So you are just comparing execution price to a constant number, basically. So when you and this market price, when you sell it, doesn't have any slippage, no matter what the volume is. The third standard or criteria to analyze the AMM is the liquidity profile, which is similar to Uniswap V2, which is how much liquidity you are depositing in each price range. But in this case, the price range can be infinitely small. The liquidity profile, the general formula for two token pool is can be written as the first equation. L equals dy divided by d square root of p. P is the relative price between relative price of x in terms of y. So for Uniswap V2, when you do this kind of calculation, you can see the L is always constant because P equals y over x, and y equals k divided by x. So d square root of p is d square root of k divided by x squared. Or yeah. For balancer, if you do the same calculation, you can see if for two token pool, if the weight is not equal, the liquidity is slightly concentrated for curve. For curve V1, if you do the same calculation, you can see it's the liquidity is concentrated in like one price range. And that's exactly what they did to serve stable coins. So you only need liquidity in a certain price range because the stable coins doesn't deviate from the peg too much. Next, I will talk about some advanced automated market makers. So first, it's a term. It's called TWAMM, which stands for time-weighted average market maker. So the difference between this and the normal constant function market maker is you have buying and selling at the same time, and for this to be closed forms, like the trading outcome equation or formula to be closed form, buying and selling has to be at constant rates, which means that you are selling at a constant velocity against the time. This is good for large order execution. So you can just execute a very large order across many blocks. And it will automatically update the state of the AMM if there's a new interaction. You can cancel the order at any time, but you will get the trade result before your cancellation, and your remaining order will get preserved. So how to do this is you differentiate first and then you integrate. So you cut your very large order into infinitely small virtual orders, and because you have buying and selling at the same time, you add those infinitely small trading results over time, and you can basically get rid of the time because of the closed formness of the AMM. So to be more specific, say you're selling token X and token Y at velocity of FT and GT. The infinite for or infinitely small virtual order dx, you first add up the amount you are putting, so ft times infinitely small time plus the amount, actually plus amount of actually it's a minus, but because dy dx is a negative number, so here is a plus. Minus a number you're selling token y into token x, like minus a number of token x you are exchanging y for infinitely small time. So for constant product market maker, you have x, y equals k. And so when you plug in the marginal price formula, you get dx divided by dt equals ft minus gt over k times k squared. And and you can do integration to get a formula without time, because the selling rate is constant. If the selling rate is not constant, the left hand side of the last formula is dependent on t, so it's so you need a relationship between time and x to convert the first to convert ft over gt to a function of x first, which is very hard to do. But when the selling rate is the ratio of selling rate is a constant, you can do the left hand side and right hand side independently. And so the result is symmetric, and and token reserves can be written as an input reserve, total input token numbers and the current reserve of token pool, and also the invariant k. So this is for Uniswap V2. For Uniswap V3, it's a little bit more complicated because of the price range. So you had to calculate your orders incrementally, because once the price crosses a price range, the liquidity could change for that price range. So you had to do it incrementally to calculate how much time it will require you to go to the next price range and calculate the end result accumulated. But the formula is exactly the same, because you can use the same formula because Uniswap V3 is just Uniswap V2 with virtual reserves. So you do everything in virtual reserves, and the you do everything in virtual reserves, and substitute and minus the added virtual reserves at the very end. So if you use this general formula on balancer, which is x to the power of alpha times y to the power of beta. Instead of alpha beta equals 1.5, you get a very complicated integral to evaluate, and this integral can be expressed as a hypergeometric function. As far as I'm concerned, so this hypergeometric function is only closed form when alpha equals beta equals 1/2. So when you do this kind of buying selling at the same time, kind of order on balancer, it doesn't work because it has no closed form solution, which is very difficult to do it on chain. Next, I will talk about routing. So for Uniswap, you have same asset fragment. The liquidity of it is fragmented across a lot of pools. So for routing, so for basically the purpose of routing is for a trade you bring the same post trade marginal price across routes equal. So to do this, you need to first solve the single pool arbitrage problem. For Uniswap V2, because you have because the fee is taken out of the trade and add back to the pool after the trade, you have to optimize for the best arbitrage outcome. So it's not simply the post-trade marginal price equals to the market price, because any price in the range of the market price divided by the fee parameter or multiplied by the fee parameter, if the post-trade marginal price is in that range, you cannot arbitrage no more. And so it's so you have to optimize it over a price range to find the best arbitrage value you can get. And when you solve this problem, you need to take into consider multiple routing. So for example, instead of selling token A for token B, you can go through say token C first, and this is very computationally intensive because there are a lot of tokens and a lot of rules to consider to go through, and this is similar to the computationally hard NP-hard problem traveling salesman problem, because so basically you're solving the shortest route between n cities when you know even you know the distance between each city, between you to each city, but when you want to solve the shortest route to go through each city once at a time, it becomes NP-hard. So I think what Uniswap did is only consider certain transaction tokens. So it only goes through like at most 4 middle tokens, and those 4 middle tokens is only the one with the highest liquidity, ETH, DAI, USDC, and USDT. So when you solve this multiple routing problem if you have a fragmented liquidity issue. The highest level of routing is a multi-DEX routing. So basically, this is a DEX aggregator. So you bring the same post-trade marginal price to every DEX to optimize for your trading result. Next, I will talk about time-dependent automated market maker. So far, the environment of the AMM doesn't depend on time. But here I introduce like two AMMs that depends on time, which has real world applications. So first is a yield space AMM, and second is a probability based AMM. First, the first AMM is used for constant interest rate yield protocols. So the interest rate can be written as 1 over the relative price to the power of 1 over t minus 1. So in this notation, X is an underlying token, say I, and Y is the principal token, FY DAI. So FY DAI can be exchanged for 1 DAI at maturation because of the behavior of this market maker. When t goes to 0, it's simply a constant. It's a constant line with a slope of 1. So at maturation, Y can always be exchanged for X at price of 1. So the interest rate therefore can be written as 1 over t to the square root of 1 over t minus 1. And the marginal price of this AMM is t equals y over x to the power of t. So the equation simplifies to y over x minus 1. So at any moment before maturation, the interest rate you get is a constant, which is the ratio of reserves minus 1. The second one is it's similar to yield space, but it's applied to prediction market. So the last equation on the bottom right corner is simply saying the price of the AMM, the marginal price, is equal to the probability of the outcome being no divided by the probability of outcome being yes, and the D is a number determined by the ratio of token reserve Y and token reserve X, similar to a binary call function, binary call option. And if you, because this a big N is a cumulative normal distribution function, because this is not a cumulative distribution function of a normal distribution. Cumulative function of a normal distribution is not a closed form. So we used some approximation function to approximate this cumulative function, which is, I believe, is n equals 1 over 1 plus e to the minus d over some constant. and when you take that approximation, you can solve the differential equation easily, and you arrived at this AMM. So basically, this is the price. The price of this AMM always tells you the marginal price of this AMM always tells you the probability ratio between no and yes. Finally, I will talk about self-financing market maker, which is what Cavalry is building for its first product. So we derive this self-financing market maker from the first principle. So the first principle being the conservation of value. So value is not created or destroyed. So and there are two parts you can separate from each other. One is the value, the change of value due to trading, and one is the change of value due to market activities or due to price changes. So for self-financing, we can set either of them to be 0. And here alpha 0 is a number of pool tokens, which is a number of LP tokens. Okay, and asset I except I equals 0 are all assets in the pool. So this can support infinitely amount of tokens permitted by the gas. If the gas is permits us, you can add infinite token in one pool. And the marginal price of this asset can be determined by the same formula used for balancer and Uniswap. So it's the value weight times the LP token numbers divided by the asset number. So everything here is everything price related is denoted in the LP tokens. One thing we found is when you apply this LP token notation, like denote every price in LP tokens, the Uniswap V3 market maker becomes a little bit simpler because you don't have to take a square root anymore, which is a little bit gas efficient. If you use the relative price between two tokens, instead of the relative price between one token to the LP token, you will arrive at something like L divided by square root of PA and PB, and L times the square root of PA, which involves square root. And UK here is a linear combination of the pre-trade price and the post-trade price. And once we have the marginal price formula, we can put it all together, and we can arrive at the general this general form of self-financing market maker. So K is a measure of how close you are to pre-trade price. Actually, how close you are to post-trade price. So if K equals 1, you are trading at post-trade price, and K equals 0, you are trading at pre-trade price. So when K equals and G here is a ratio of the new reserve divided by the previous reserves for every asset. So note here, it's everything is measured in the growth rate of the tokens instead of the absolute difference between the previous reserve and the new reserve. This also has implication that this is not a constant function market maker, but path dependent market maker, which means it's like when when you return to the same when you return to the same reserve numbers, you can incur some loss of gain compared to Uniswap V2. Uniswap V2, the impermanent loss is always 0 when you go back to the same reserve number. So this is a little bit different because we measure everything in growth rate of the token reserve, which means this is a path dependent AMM. So key takeaway from this is we decompose the execution price as a linear combination of the pre-trade price and the post-trade price for every asset. So when you have K equals 1/2, you arrive at something magical happens, and you can simplify the swap function of assuming there's no depositing or withdrawing liquidity, which means G0T equals the growth rate of the LP token is 1. And you only swap 2 assets, so the other growth rate of assets is 1. And you arrive at a constant product market maker, which is Uniswap. When K equals 1/2. So basically Uniswap use the execution price of its pre-trade marginal price and post-trade marginal price. Use the mean of the pre-trade marginal price and post-trade marginal price. And another advantage of thinking this thinking in terms of values instead of thinking in terms of token reserve number changes is you can have 1-to-n or m-to-n token exchanges. So m-to-n token, if you swap m tokens to n tokens, you can just calculate the total value by the those m tokens you put in, and you give an allocation percentage of how much value you want to go to for each of the n asset going out. And you can calculate how much value you get allocated for each asset. Each asset you are swapping for those n assets. This is very it's very useful to think this way. to enable what we call multi-swap. So even on staking or staking or depositing or undepositing liquidity can be thought of as a multi-swap, and this also enables single-sided liquidity staking or partially sided liquidity staking, because you don't have to provide all of the assets in equal proportion. You can just provide some of the assets you have, and the staking process is simply a swapping. It can be thought of as swapping first and deposit of the new balanced portfolio in the balanced portfolio proportion. So that's it for me. Hopefully you learn something about automated market makers today. I will take questions from now.
So thank you. So there are some questions in the chat, but does anyone have any questions before I go through them? All right.
Is it first?
Yeah, so what kind of properties do we expect AMMs to have, and how do different AMMs compare with respect to these properties?
So AMM is just like a mapping function between the old state of the reserve and the new state of reserves. So it can be any like function in general, but you want some slippage for swapping one token to the other.
Mm-hmm.
And different AMM have different way of handling fees and their slippage. For example, Curve V1 doesn't care about doesn't care too much about slippage, so they amplify the constant sum market maker part.
Okay. Yeah. All right. Another question we've got is, do you see order book approach replacing AMMs in future DEXs?
Okay, do you see order book approach? I don't think so. I think recently some I think people at H16Z crypto posted a comparison between limit order books and automated market makers, and they found they are so Uniswap V2, for example, is very similar to limit order books, but much more much more simple. If you took order books, it can have more functionalities, but you have so basically what they use is a number of basis functions to how many basis functions you need to cover like any liquidity curve, liquidity demand curve.
Mm-hmm.
So they found although AMMs have limited functionalities, their basis functions is their advantage is the number of basis functions is much less compared to limit order books. So they have both advantages and disadvantages.
Okay. If you can stop sharing your slides for a sec, I'll go through the future talks. Okay, I will quickly share the last slides. Okay, I know we're heading towards time, but so in the coming weeks, so next week at 5 p.m. Brisbane, we've got a talk by Dominic about Polygon Midden or Midden, and it's a zero knowledge proof chain, so a ZK rollup. So it should be interesting. We've got Oliver from Zelic talking about how they do contract auditing and the process they use and how it works. Sriram is one of the leaders for EigenLayer, and so he's going to talk about EigenLayer, and then I'm going to talk about how well I've gone at solving or finding bugs in Solidity code using AI, and how I've gone about doing it and what I found to be successful. And there are some more cross-chain talks. If you're watching this on YouTube, there is a meetup, and if you're, there is also the YouTube channel. Swaggy is coming. So I've, over the weekend, banged together some swag. I've done a trial order for myself so I can see whether the positioning and the code and the quality of the t-shirts is good, and if it all has worked out. And once I've assured myself that it all looks good, then I'll launch the swag channel. The idea is to sell the swag at cost price. So hopefully people can have a bit of fun with that. And with that, so that's all. And so thank you, Leo. That was a really interesting talk, and I learned quite a lot. I don't think I understood every formula, but I think that really helped my knowledge. So thank you.
Yeah, thank you for inviting me to this talk.
Yeah, no problem.
And you can.
Yeah, go ahead.
Yeah, you can reach me at the Twitter handle at the very last slides. If you have any questions, I can send you references as well if you want to learn more about automated market makers.
For sure. All right, awesome. So I'll post this on YouTube, and you'll all be able to see it in, I don't know, maybe a few hours, worst case tomorrow. All right, thank you, everyone. Bye-bye.